Thank you very much. So thank you also to the organizer for letting me presenting my work. So the title is quite mysterious maybe for some of you, but I will speak about some impacts of drops and the way they freeze when they impact on a very cold substrate. So this work was done originally at Institut d'Anvers, where I was until 1 year ago, which is in Sorbonne University. And my two collaborators, so Thomas Seon and Virgile Thievna, which is a PhD student of Thomas and me, are still there. And I'm now in l'ADIX at Ecole Polytechnique. So let's say what are the motivation or the context of this work. Actually, we were, our original question was quite general. What makes a drop if it impacts on a very cold substrate so that it can freeze? So our original motivation was, can we have a coupled dynamics where the freezing can be as fast as the dynamics, or do we have a coupled dynamics that can change a little bit the impact phenomena? There are also some application of that I can think of. Actually, there are some work done by the group of Chandra in Toronto for maybe more than 20 years, where they look for impact of molten drop of metal on solid substrate. So then the substrate is at a temperature which is a temperature where the metal would be solid. And then you can see that as the drop impact, you have both a solid part of the drop that part of the drop is solidifying while the rest of the drop is still liquid, and you have an interaction of these two dynamics. Now also an application which actually will not be really my work or work will not really be an application of that. We could not apply what we have on this directly on these things, but we still believe that understanding the impact of a drop on a cold substrate might be of interest for that, which is a very important industrial aspect of freezing, which is the freezing of airplanes, which is due to the fact that you have ice in the clouds that can impact during the flight the plane, and they can stick on the plane, and they can really make higher real problem on the part of the plane. Sorry. Actually, if we look carefully of the condition at which these are happening, they are not at all the condition I will be looking here in my experiments and the theory. But still, we believe that understanding in a better way how solidification process interact with the dynamic of drop impact might be of interest even for this application, which is a little bit outside of our work. So let me show you first an experiment that we did just to show you the mechanism. So you have a drop of water which is impacting on a solid substrate, which is metal. You should not worry too much about this line, which is due to the fact that we try to make it as smooth as possible, and we have not reached the smoothest things we could. We did it better after this movie, and it does not really, even if it looks quite bad, it does not really influence the dynamics. So the drop will impact, and as the solid is very cold, you can imagine that at the contact, you will have a very thin layer of ice that will be formed, and then you will observe the dynamics of this impact. So you see the drop impact we don't see very well. It reached a maximum radius, and now you can feel, I will run, you can see this film of water that is retracting on the ice layer. So let me show it again. So you see, let me rephrase what we have seen, and then I will show again the movie. So the drop has impacted. Then, if you look carefully, it does not move for a small amount of time, not so small. Which means that because of the ice that has been created, the impact is stuck at the maximum diameter. If you would do the same impact on a substrate at room temperature, you will have the spreading and then the receding phase. And the two phases would follow each other without any waiting time. Here, we will observe a waiting time before the water would retract on top of this ice layer that has been formed at the impact of the drop. And then this drop layer will create this very nice shape. So the liquid layer retracts and form in that case this nice rim that is frozen at large time because you have a stop of the retraction. Let me show you again the movie, and I have other figures. So you see, then it stops, and then you will start moving now. It retracts, and for some reason that I will not explain here today, we are still working on it. At some point, the solidification has grown faster in the middle than here, so that the water is trapped in a circle in between, not in the center of the system. and you end up with a very nice shape, which we call the donut shape. Actually, it's not exactly a donut shape. You have almost a pancake on top of which you have a semicircle of ice. And you know it takes a long time to solidify all this.
So we can see through the thin film, it's not white.
Yeah.
Why? On the edges.
That's a good question. I think, but I have no. I think that in some sense here we have what people call a driven solidification. So in one direction, right here you have maybe a solidification which is more hectic. But you know, in some sense, it depends how your ice is growing. And I think here you have a oh, everything is water.
Yeah. And there's ice right to the edge. You see an edge. That's what I
You know, you have ice from here to here, but what he says is that the ice here looks white, while the other one does not look white.
no ice in the middle.
Oh, there is ice in the middle. There are the same ice in here. Sorry. My understanding is that here you have a driven solidification, or here you have a bulk solidification with some maybe different. You know, ice solidification is quite a difficult process. I'm not sure. Actually, I have no clear idea about that. But that's true. We have this.
Could it be simply a question of thickness?
Maybe also.
Much thinner.
Yeah. But that's true. It's also very, yeah. That's why we don't have a clear understanding of that. We should maybe make an experiment where we really look how thickness of water look as the thickness is evolving, thickness of ice. Could be. We haven't thought a lot about that, actually.
Do you have a clear understanding of the waiting time?
Okay, that's my talk. Okay, so what did I show you? So just to give you some hints about the experiment. So I'm not an experimentalist, so I'm giving you the information my colleagues gave me. So one of the difficulties, so how do we reach a very cold substrate? We took the substrate, the metal, we put it inside nitrogen liquid, and we wait until it reaches a very, very cold temperature. And then the time to recover the room temperature is very long so that you can make experiments. And during the time of experiment, which is less than 1 second, the temperature of the substrate does not move. So, exactly. We have to avoid moisture. That's the real issue of the thing. So we do that in a controlled chamber. That was the real issue. If you do the experiments here, you will have very rapidly, particularly in Singapore, a lot of moisture on the top of your solid substrate. So you're dead. You're not dead. You will see something interesting, but something that you don't want to see. So here we had to the main effort was to control the atmosphere. So you make it in a chamber, in closed chamber, where we were filtering the moisture in order to make it as small as possible. So we vary the impact parameters. That means the drop velocity, the drop radius, the substrate temperature, and also the substrate. You will see we also change the substrate. And actually, I will discuss today 2 problems. First, trying to understand what is the typical ice layer that we form. And also, I will finish with some work that we did 2 years ago on the stability of the frozen drop, if I have some time. Pardon?
Is the ice amorphous or is it crystalline?
It's crystalline, I think. That's an important point, actually. That is in the things we want to do in the future. Definitely for the metal, at least this metal is definitely amorphous. Or at least we would like, maybe not this one, but we would like to make the same experiments, particularly in the stability process, if you do it with amorphous materials, compared to ice, which is definitely a brittle material. This one, what I want to say is that this one, I think, is not a brittle material. It's more plastic material. Okay. So let me show you another experiments done with different parameters, and let me show you not a movie, but the different snapshot. So the drop is impacting on the substrate. So you see, it's a recent experiment, so we have improved our way of fabricating a smooth surface. So the drop is spreading. As it spreads, it reaches a maximum diameter. Then after it reaches the diameter, it remains still for a given amount of time until it recedes. And as it recedes, instead of making the pancake that I called last time, it makes a kind of eggs fried shape. So here, the ice is not this circle thing, but it's this half sphere that is formed in the middle. It's just a question of how you retract compared to how the ice grow. That's the thing we are looking for. And again, coming back to the remark of David, when you solidify so here you are still liquid, here you have liquid, here you have ice, but as this liquid is solidifying, you end up with something with a different color, which I'm not sure I know why this color is different than the other one, maybe just a question of thickness, as David suggests. Okay, so we'd like to understand that. So as you mentioned, we can measure, we can measure the radius as function of time, but not the radius of the ice system, but the radius of the liquid one. So as you can see, and we did it for 3 different temperatures. One is the room temperature, the red curve. So the red curve is the easiest one to understand. You have a spreading phase, and then retraction. And almost here you have something which looks flat, but it's just a question of measurement. So basically, the dynamic is continuum in the sense that you have retraction, expansion, retraction. And there is no stopping or waiting time in between. On the other one, when you do the experiment with -7 degrees, -24 degrees, what you observe is a different dynamics. You have at short time, you have almost the same dynamics. You can see that there are some difference in the maximum diameter. So the freezing change the maximum diameter. But if you forget about that, you have something which is very similar at short time. So the spreading is almost the same. But after it reaches the maximum radius, it almost stops, and actually there is a very small receding, almost a constant time. There is a waiting time which is between this and this one. Here I call it the residence time, but it's a waiting time, during which the expansion of the liquid layer is almost not moving, at least moving very slowly. And then suddenly it retracts. So here when you change the slope here, it's when the liquid layer starts to retract. What is interesting also is that the retraction dynamics, or the retraction velocity, seems to be very similar if you have retraction of water on ice, while if you have retraction of water on the substrate. So in some sense, the dynamics of retraction seems to be independent of the temperature and independent of the fact that you have ice or substrate. Probably it's related to the contact angle that's probably the same on the ice and on the substrate. But it's important to see that the retraction dynamic itself seems to be independent of the temperature.
If you ask a chemist, he will tell you that the contact angle of water on ice is 0 degrees.
Well, some say 90 degrees.
But this water is not so pure.
That's that's an interesting question, because we thought about that. There are some people that say that if it depends on which condition. The problem is that water on ice is a very difficult question, the contact angle, because you are not at equilibrium somehow. So particularly the ice, it's very cold. So it's not an easy thing to define. What people observe, for instance, there was an experiment, a quasi-static experiment at MSC in Paris, where they, by some reason by making some argument on the heat flux at the contact line, they were arguing that the contact angle should be 90 degrees. And I think when they measure it at 87. So, and we are probably closer to this 80-something degrees than 0. And I have no clear understanding or clear explanation of that. David?
Just what you just said remains valid. The water which is coming is hot. The weight is very large.
Yeah, the water is about 20 degrees when you make the impact. Yeah. I don't know. You will see in the model, in the model that we derive after, we neglect the temperature of the water for the reason that the energy you need to make this water going from 20 degrees to 0 is negligible compared to the latent heat. But, negligible means if you are 100, it becomes less negligible. But that's one of the arguments to neglect, for instance, the heat transfer in the water. But could be interesting to check. Okay, so we could then measure this waiting time just to see how it evolves as you change the temperature and as you change the drop impact velocity. And we observe something which was a little bit surprising for us, which is that this waiting time, for instance, if you have a large impact, that means a large velocity impact, does not depend on the temperature. So everything is as if this waiting time during which the liquid is stuck by the ice layer is almost constant. If you have a smaller impact velocity, you see that you have some kind of a transient at low temperature, but still it does not depend on it reaches a plateau, and this plateau depends on the other one on the impact velocity. I will come back to that because we have not a clear explanation of that. We have some ideas about how to explain that, but it does not fit. Our ideas does not really fit with all this data. Here I'm using delta T. Delta T is not the difference between the drop temperature and the substrate temperature. It's the difference between the substrate temperature and the melting temperature. For the reason I explained to David, we neglect the fact that the water has to go from 20 degrees to 0 degrees because the energy for that is negligible compared to the latent heat. So the pertinent temperature difference is the one between the substrate temperature and the melting temperature, which is 0 degrees here. Okay, so we are able, when the drop is totally frozen, we can with a laser make a map of this drop, and we have the solidified drop look like that. So in the case I show you the last case, so you have a pancake layer, which is this HP that I will study here, on top of which you have this structure that has been created by the retraction of the liquid layer that was still not frozen when the retraction started. So what I would like to study today and to get interested today is what determines this HP. What are the characteristics or what are the physical mechanisms that determine the value of HP? So you see that HP can have a lot of interest because you have a very elongated structure, and the stability of this structure in terms of mechanics really is the same problem of having a thick plate of thickness HP. So HP really will be an important parameter to understand whether this frozen pattern will be stable or not, or will remain stick on the substrate or not. Yeah.
Are you thinking of H as being constant? Doesn't it evolve with time?
Oh, but yeah, sure. That's the point. That's the point we discussed. But what here I'm at late time where everything is frozen, and when everything is frozen, this is the scan of the dead situation where everything is frozen. So when everything is frozen, we observe this shape. And what I make is that in this shape, I decompose this shape in one which is a plateau things or a pancake thing, on top of which you have the water which has retracted and then frozen.
I see you have a picture of it completely frozen.
Sure.
It just happens to have that.
You know, when you wait long enough, you are here. And actually, when you are here, you can make this scan. Actually, you cannot make the scan before because the scan is longer than the time of the experiment. So you can all.
You have a side view.
Oh, this is the side view somehow. This gives you the side view because this is a scan by the. Exactly. You will have exactly this side view.
Some colleagues of mine and I looked at it, no impact, put a drop on a cold plate, and when it freezes, you get a cusp.
Sure.
That doesn't, well, right. But
Exactly.
you said that's not frozen.
No, everything is frozen here. Now everything is frozen. This is the scan is made. The scan is made when everything is frozen. You know, we cannot do it before.
Okay.
Before you cannot do it.
You do get.
Yeah, very small one.
Yeah.
Exactly for the same reason of your colleague. Exactly for the reason actually that tells you that the angle between the free surface and the frozen front should be 90 degrees. Actually, that's the way they can. It's not necessary. You're right. Correct. You also need the change of volume. Okay, so if you measure now this HP, so we can change the temperature difference, and you can also change the substrate, and you can measure this HP defined in a very in quite a we decide to define HP as this level of residual, what you call the residual ice layer, and if you measure it for different substrate, you obtain these things. So these curves are interesting for two reasons. First, there is an obvious dependence, which is as you increase the temperature of your drop, you increase the thickness of your ice layer, which is something expected because the cooler you are in the substrate, the faster you will grow the height. So you expect the thickness to be bigger. On the other hand, you also see something that could be expected, which is the fact that this thickness depends on the solid. which is also something that you can understand, which is that if the solid can transmit heat much easier, for instance, for copper, it will freeze the water much easier than for the marble, which is not conducting heat as fast as copper. So we have something which is obvious, but which is expected, but can we understand a little bit more of that? So for that, I will introduce a 1D, what I call a modified 1D Stefan problem, or Stefan problem. So basically, we assume that the solidification is due to the heat diffusion through the substrate, from the substrate through the ice until the interface between ice and water. So you know this is something that is, in an idealized way, is called the Stefan problem. The Stefan problem is something which is a little bit different. You suppose you have ice on your right, water on your left, and you see how this front is evolving by fixing some boundary condition to the temperature at -infinity and +infinity. Here we have something which is a little bit different because we have a solid. So the solid has its own heat equation, the ice has its own heat equation, and the water has its own heat equation. And you have some boundary condition in between. And the idea is to say, okay, I will try to write everything as a heat equation in 1D because my system is elongated, so I will first neglect the 2 or 3D effects. And I will try to write this system. So you will see that actually to the best of our knowledge, written like that, we haven't seen it in the literature. We have looked to a lot of paper with Stefan problem. We haven't looked to that. We haven't seen something like that. So basically, we have the substrate, we have the ice, and we have the water. And what are the equations we want to solve? So as I said, I will simplify a little bit more my problem by not considering the heat transfer in the water. I will suppose that the water very rapidly reach 0 degree, the melting temperature, and I will neglect the heat transfer in the water. It will not really be difficult to take into account, but it simplifies my calculation, which is already not so easy. Basically, in the ice, I have the heat equation with the diffusion coefficient of in the ice. In the substrate, I have the heat equation with the diffusion coefficient in the substrate, and I have some boundary conditions. What are the boundary conditions? If I am far away in my substrate, I need to have that the temperature is a constant, is the temperature of my substrate. Oh, sorry. If then at the interface between the substrate and the ice, you have two boundary conditions. One is not written, which is that the temperature has to be the same, but it's an unknown. You don't know what is this temperature. On the other hand, you have the continuity of the flux. The thermal flux that goes actually from the ice to the substrate has to be the same in both when you compute it in both sides. On the other hand, at the solidification front, you know the temperature. It's constant, but since you have fixed the temperature of water to the melting temperature, the temperature has to be the melting temperature, and which is a little bit simplified compared to the real Stefan problem. And here, the heat flux coming from the ice is exactly compensated by the growth of the ice layer. So, which is something. In some sense, this is a Stefan problem, but where we have a little bit changed the position where we put this condition. So if you look to that, as you know, in such Stefan problem, you can often have a self-similar solution. What is interesting in this problem, which is a little bit different, since we have three domains instead of having only two, we keep the self-similar property because, as you know, so the self-similar solution of the heat equation goes like Z goes like square root of T, you know. But also, since the solidification front in this limit is a diffusion front, it also goes like square root of T. So it does not destroy your self-similar structure of your solution. And to be more precise, I think. And it will give something which is called a transcendental equation for the ice layer thickness, and I will explain you more in detail. Yeah. So basically, you can make the assumption, or actually you can prove that if you look for self-similar solution, it should have this structure. So the temperature field should go like Z over square root of T. And actually, the height of the ice layer should go like square root of time with the coefficient of diffusion, an effective diffusion coefficient or effective growth coefficient, which is exactly the thing we would like to understand. Because if we are able to solve this problem, then since we know the time of residence or the waiting time of our drop before it retracts, then we will have an idea of the residual thickness we want to find. I introduced this definition of the air function. It's not always the same for everybody. And basically, if you put that in your equations before, in actually my two equations, basically my two equations here and here, you end up with something which is quite known, which is that you have two self-similar solutions that goes not as z over square root of t, but in each part, for instance, in the substrate part, your solution is the classical F solution with z divided by square root of ds times t. And in the ice layer, you have a solution that depends on z over di of t. But you have some constant of integration, and this constant will depend on your boundary condition, which are not trivial here compared maybe to some case of the Stefan problem. No, it goes from that's the difference compared to the Stefan problem. My eyes go from 0 to h of t, because after you have water. Exactly, and you're right. That's why you cannot find. That's why you have a transcendental equation, because you have to find a solution that you have really to compute the flux in the self-similar variable, and that.
But then thermal diffusion is the substrate and the ice. It's effective both.
Yeah, exactly. Yeah, that's why that's a way of qualitatively understand why you freeze faster when you do the impact on copper compared to marble. Why they are all at the same temperature is the same reason why when you put your finger on copper or on wood, you feel that you think that this thing is cooler than this one. It's not cooler. It's just that it takes your temperature faster. So you have these two self-similar solutions, and we need to basically we need to solve A, B, C, and then having A, B, C, we need to solve also to find df. So the unknown for us somehow is df through A, B, C. So just to make sure that you understand what we are solving, at the end of the day, the solution we will find is this one. We have a temperature in the substrate that goes like an F function, which is a self-similar solution. So as time goes on, as it spreads here. In the ice, you have the same type of F function, but with a different expansion coefficient di, or instead of ds, but it goes as well like square root of time. And you have some boundary condition. Here you have that the flux should be continuous. I mean, the figure is not correct because the slope should be different here, because the flux should be constant, should be continuous, but not the slope. And here also you have that the flux here is exactly responsible of the growth of the ice layer. So that can be put in as boundary condition for our system. So you have two boundary conditions to apply at z equal to 0. So you have to apply that the temperature of coming from the solid is the same than the temperature coming from the ice. So it gives you this condition. And you have the continuity of the flux that gives you things, which introduces you something which actually I didn't know until 2 years ago. I think it's not taught anymore, at least in France, which is the effusivity of the material. I don't know if you have heard about that. Effusivity of the material is exactly these things, the fact that you feel something different if you touch wood, or it definitely gives you how much your system is reacting, is transmitting the heat. Then you have another condition which is at the moving front, which is going like square root of, sorry for that, df of t, and you have these two boundary conditions. So you see we have 4 unknown, A, B, C, and df, and with these 3 unknown, we have 4 unknown for, sorry, and df, and we have 4 equations, so we are happy we can find a single solution of that. And actually, this single solution, that's where we get this transcendental equation. We got this relation between the square root, between the ratio between the effective diffusion and the ice diffusion. We have this implicit relation, which is a transcendental equation. You can solve it analytically. And you have this relation, and it involves the ratio of the two effusivity and the Stefan number. So actually, this equation has been obtained in different cases where people were supposing, for instance, that the solid, if you, for instance, some simplified model introduced by Gray-Roster was taking the substrate as a constant temperature, imposing the temperature of the substrate equal to Ts everywhere, so until the interface. So a way to understand that would be to take ES going to infinity, so you neglect this term here, and then you get the same result as Roster if you take this thing. But here it's a little bit more complex situation. Okay, so you can solve this equation numerically. So then you can obtain df as function of the Stefan number, and Stefan number contains the difference of temperature. And you see that, and you can show that analytically, that at low Stefan number, the ratio between the effective diffusivity and the ice diffusivity goes like delta t to the square. And that can be shown by taking the limit of Stefan number going to 0. Okay, so let's come back to our problem. So you remember we measure some dependence of HP as function of delta t for different substrates. And we observed this curve, which were we were happy with this curve because they were intuitive. You know, they were increasing as the temperature the temperature difference was increasing, and they were increasing as the substrate was more conducting heat. But if you now, what is interesting is to compute hp square. No. Sorry. hp square as function of alpha, which is my df actually. And what do we observe? We observe something interesting. We observe a straight line. We observe two things interesting. One is we are happy with, which is the fact that for the three different substrates, the curve collapses. What is maybe less expected that it collapses on a straight line, at least for small enough effective diffusivity. Which means that if you remember, the ratio between these two numbers is a time. So there is everything. The fact that it collapses on a single line means that there is a single time. So, and this is exactly, it reminds us what we observe experimentally, which is that we have a waiting time before the retraction of the liquid appears, which is almost constant. So we would like to check whether this time that you can deduce from this curve is the same as the waiting time that we can measure by another way. So that's exactly what we have done. So basically, we have done experiments by changing now both the substrate and the speed of impact. And by doing that, you can rescale everything. So now you can rescale hp squared by the waiting time that we have measured independently. And you compare that to the effective diffusivity that we computed analytically, or not analytically, but by solving our transcendental equation. We observe something which is compared to the spreading of the spread of this data, which are quite good in the sense that it almost collapses on a single line. What is a little bit more surprising is that it does not collapse on the line. The slope should be 1 at the end of the day. If we believe in our model, the slope should be, and the slope 1 is this one. And you see that we have a slope which is, we have a factor of 2. And right now we have no clear understanding of why there is a factor of 2 instead of 1. So that means that you freeze faster than the model suggested. So there could be two reasons. First, we should maybe redo the calculation to make sure that we did not lose a factor of 2 somewhere. That can always happen. The other thing is that, we have a 1D model, and the 1D model, in some sense, underestimate the heat flux coming from the substrate, since you have now, you can have heat flux coming from the edge of the substrate. So it's not easy to understand why he makes a factor 2, but it could be an explanation. Yeah, we have no idea. We have no idea that could really be testable. That's the point. We have some clues, but we have not. Yeah, we have no clear idea how things are working out. That's true. Our model is really simplified in the sense that we take infinite size for the substrate. So it could be. There are a lot of things that. Cool. Let me show you, because it's a work in progress, some open question that we are looking at right now. So we exactly as you say, we would like to understand the limitation of the model in order maybe to understand more where the model, where we can trust the model and where we should be careful about that, particularly for instance, for large temperature difference. There is also the finite size effect and the 2D effect that we should see. Actually, as you asked at the beginning, there is also, we should try to understand why there is a residence time which is almost constant, a waiting time which is almost constant. We were quite happy to discover by a group of, during the thesis of Michael Benzakem and Eli Raphael, they were looking to a situation very interesting where they were suddenly creating a very thin layer of liquid, and this not cooling that time, but by heating polymers. And what they observed is that there is a very slow relaxation of the contact line, which goes like T to the power 1/4 and all that stuff. And we are thinking that maybe that could explain exactly what we have here. We have the drop that is spreading. Then it's stuck by the contact line, but then it's stuck with a moving contact line, which is almost at 180 degrees. And then this moving contact line has to retract until it reaches the receding angle, at least at which it can start. So that, at least, would not depend on the temperature, and we could say, okay, we have an explanation. But actually, if you think a little bit more about that, it's more complicated than what I say, because that should depend, this time scale should depend on the thickness of the liquid layer that is created. And the thickness of this liquid layer should change change with the impact velocity, which is okay because we see that our waiting time changed with the liquid impact, with dropping. But it changed also with the temperature, because with the temperature, the liquid film that is created at the time where you start this process should be different, because you have solidification which is different. So we still need to work a little bit more on that to make sure that it can work. Maybe there is a combination of these things that makes that at the end everything works well, but we need to work more on that. We need to understand a little bit more about the retraction velocity, which seems to be independent of the temperature. That means we see almost the same velocity as you retract on these substrates and on the ice. And as you say, there is things to understand about the moving contact line and the moving contact line dynamics, and what are the thing we can. Maybe you're right with the 0 degree, but you have some advancing and retracting contact angle that should be considered. I have no clear idea of that, but definitely, this is definitely something we want to understand more and maybe to measure more. And actually, the things I would like to show you right now, if I have 10 minutes, is something we did first, which is the stability of the structure toward thermal stress. And this is the first, when we work on this problem, this is the first thing we look at, which is to, you see, what I show you until now is the movie until it freezes, and then for the first movie I show you, until it was frozen, nothing moved anymore. Things are a little bit different if you do it at cooler temperature, minus 30 degrees. Look, we have the same impact than at the beginning, waiting time, then we have this retraction. This retraction because for some reason the growth of the ice layer here is faster than the retraction, so you have this. And everything now is frozen, and you think that everything is finished. And you will see, and actually, as Lei said this morning, this is not a photo, this is a movie. So nothing moves. But you will see that suddenly, okay, you have seen something like that happen. It explodes somehow. It breaks. Okay. No, this altogether was 2 seconds. No, it's let's do it even at higher temperature or lower temperature, but higher temperature difference. You see even something different. Now you see that you see cracks appearing before, and now you see the retraction of the liquid. So now you see crack appearing before the total freezing of the structure. And in that case, the cracks are quite different. Instead of having an explosion in one second, I mean, an abrupt creation of all the cracks are created one after each other. And in that case, this is quite reminiscent of a lot of figures you can see when you have drying of structures. The cracks are almost at 90 degrees once compared to each other. So when a crack is created, it relaxes the stress in some direction, and then it's more brittle in the other one. And that reminds the question that you asked. So water is brittle in the sense that it will break instead of deforms under stress. And if you do something which is in between, you get something which is, you see cracks appearing, and then suddenly what we call fragmentation, which is the explosion, and you see still water on top. So I will just explain you how we explain that. And actually, we are able to, so just you see that as for this case of impact, as the temperature is varying, as you go to cooler and cooler substrate temperature, you have nothing that happens, no cracks, so you can keep that as long as you want. Then fragmentation, so the crack is freezing, totally frozen, and then you wait, and suddenly it breaks. Or you can have cracks appearing during the solidification process. And you see that these patterns are very different than this one. Okay. So we have a phase diagram, but I think I will go. So these things is reminiscent of something that we call the Prince-Rupert drop. I don't know if it's Prince-Rupert drop. So there are a very famous drop of ice that you can, if you create a drop of glass, sorry. So when you create glass, if you take very hot glass, you put it in the water so that it solidifies very rapidly. Then it's very brittle in the sense if you give a small, so this thing seems to be very, very strong if you hit it like that. But if you break a very small amount of the tail of these drops, then it explodes very rapidly. So the idea is that in these drops, there is a lot of residual stresses that have been created during the solidification, and that can explode. There is also an experiment that was done a little bit after ours by the group of Loser, so Wiedemann in 20. They did something very interesting. They solidified the drops by the external. So they create the ice at the at the exterior of the drop, so that the drop is freezing from outside to inside. So as it goes inside, since the volume of the ice is bigger than the volume of the water, you create more and more stress inside, and then suddenly it explodes. This is exactly what they observed. Okay, so now we have some clue about what are the fracture mechanisms we want to understand. So basically, to make it very simple, because I think I have only a few minutes, when the liquid freezes, you can assume that the liquid freezes at 0 degree. So that means the pattern is formed at 0 degree. The solid structure is formed at 0 degree. But since the substrate is at a much different temperature, the substrate still continues to cool the solid structure. So that means you have a structure that has been created at 0 degree, but then its temperature will change as function of time, will decrease as function of time. And we know that when we cool a solid structure, it will shrink, it will retract. But since you are blocked since our drop is stuck on the solid substrate by adhesion, it cannot move. So that means you will create thermal stress or elastic stress in your system. And if the elastic stress are big enough to create cracks, then you will create a crack, preferably to have elastic stress. So this is exactly the classical theory of what we call the Griffiths theory for cracks. That means you can compare the energy. You can compare the energy that is due to elastic deformation in your system, and you can compare it to the energy that you would need to create the cracks. So you know that creating the cracks means creating a surface, and so that means it costs you some energy by surface, while the elastic energy is on the volume. So you see that immediately you have a length scale that is appearing. Okay, we can put that a little bit more in equation. So basically, if you take the thermal strain will be alpha times delta T. If you take a classical elastic elastic system, you have the elastic energy. You have the thermal strain tensor, which is proportional to delta T, with alpha the thermal expansion coefficient. Then you can compute the elastic energy of that, which is just the product of that times the deformation, and you obtain times the stress tensor. And if you are in elastic limit, the stress tensor is proportional to the strain tensor by a factor E, which is the Young modulus of your system. And if you integrate it by the volume, you obtain this dependence of the energy of the bulk as function of the size of your ice system. And if you compare that to a surface energy, which is you create two surfaces of surface L square. So you have a 2gC L square, which is your surface energy if you want to crack it. And if you want to balance these two energy, you obtain a critical length, which is called the Griffiths length sometimes, which is a ratio between the Griffiths energy and our temperature difference. So basically, this Griffiths length tells you that if what you are looking at is smaller than this length, it will remain elastic. Elastic deformation is favorable. On the other hand, if your system is bigger than this length, you will prefer to crack instead of keeping the elastic deformation. So if we do that, actually, and I will stop by that, it gives us a good way to understand the things. In particular, what is interesting is that you can compute the energy of the frozen structure when it reaches the substrate temperature. And by doing that, you can redo the same argument of fragmentation. I just want to show you how we can explain the fragmentation. So if you measure the energy of fragmentation by saying that the small pieces of the fragmentation have the same time scale, have the same length scales and the thickness of the pancake that we have measured, you can basically make the argument, and it gives you what is interesting. It gives you a threshold temperature, which is exactly 26 degrees when you put numbers inside that, and we observe in experiment 25 degrees, which I think might be a little bit of luck, but that's it. And we can do, and I will go a little bit faster, we can also understand when the cracks are forming by the same theory, but I will finish only by showing you, maybe it's better. Actually, we see cracks, but in a paper published last year by the group of Varasani and De Ritter, they observed that depending on the type of liquid that you take, here it was molten tin. Instead of having cracks, what they observe is delimitation. So there is also, the way the system can be unstable is also delimitation. And I think I'm finished, and I will just show you. We just finish with some open questions about these things, for instance. We have a splash at very low temperature, and you see that this splash, if you go to higher temperature, this splash is created by the low temperature impact. That means that if we do the same impact at minus 10 degrees instead of minus 60, we don't have splash. So this is a new scenario of splash, and you can see very interesting things, the cracks, and you have these droplets that have been frozen here. And thank you very much for.
Cool. Questions?
Cool.
In your calculation about the cracking, you had some, try to read your fingers when you explain the, the lateral, the size you assume. So you assume that the crack distance, the distance between cracks is the same as this.
Yeah, so for the, you see that we have two types of cracks, two types of cracking, crack formation. One is what we call the fragmentation. And for this one, what the argument we made is you have a very thin, you have something which is very thin. Maybe you have something on top of that, but let's forget about it. And basically, in that case, what actually we look to some people working on fragmentation. In that case, what you expect is that the size of the typical pieces of fragmentation is about the same.
Because in some of your experiments, that was not the case, that the cracks were relatively
Yeah, but that's the other one. That's the what we call the hierarchical formation. In that case, it's in some sense the case where you have fragmentation is a very specific one. You first freeze everything, and then your system is very stable somehow. So it store elastic energy, and when it explodes everywhere. So in some sense it reached the smaller scale it can achieve. The other one, you still have water on top, so there are the formation of cracks probably due to some different things. So in some sense it's, but that's the thing we should look a little bit more carefully, because people which are experts in cracks would probably not totally follow me on that. So that's the way I understand it. In one case, because you don't have any more water, in some sense your system is really storing energy until it explodes. The other case, for some reason, it explodes much before. And also the other reason is that here HP is much smaller than LC. Oh, no, sorry. It's about the same time. It's about the Griffith length. While in the other case, the Griffith length is much smaller than the liquid thickness. So there is a difference.
Once the drop spreads, does a nucleation of ice represent a problem, or is it just a continuous layer instantaneous layer formation?
So, yeah. So the most honest answer is I don't know. And we are looking to that. We are looking particularly, actually we are not looking exactly to the nucleation, but we try to understand, and actually there are some work also by the group in Paris in MSc about the advancement of the contact line with solidification. So we haven't seen any, nucleation, I think we are not able to see it. But what we would like, what we seem to see, particularly in this case where you have splashing, is that in some sense, one of the questions is that in the expansion, what is expanding? Is it water which touch the solid and then make ice and so on, or do you have water that go faster than the solid formation? You may have, where is the solidification front compared to the spreading front, for instance? And it seems that the main difference when you're splashing is that you inverse the priority of these two. But really, we have no, we need to make more experiments on that.
This is a very quick question.
Yeah.
So, in solidification, when we're talking more about not just water, but things which is a two-component system, then solidification is completely different in terms of the undercooling, the effect of undercooling. Have people done experiments like this in liquid containing, say, some solute?
So actually, there are two answers on that. First, there is actually for the impact on for the application for airplane freezing. Some people believe that the drop that impact on the airplanes, if they are still liquid, they are undercooled liquid. You see that means they should be solid, but they are. So there are some experiments done by the group of Tropea in Germany where they do really impact of undercooled liquid on soil. We are not in this situation. Sometimes we believe we have seen something which is close to that, but we avoid a little bit that. For the case where you have the liquid made of two species, for instance, grey roaster work a lot on that. This is the thing that happened on icebergs, where basically iceberg is made of ice of almost pure water, while the water of the sea is salted. And then you have a lot of nice things related to this change of dissolution property. But we haven't looked to that.
The applications, the big money application of this today is actually additive manufacturing.
Yeah, I agree.
That's where it's more than this.
Probably, yeah.
Hot water. Okay, so thank you very much.
Thank you.